Good day, all. My name is Michael Riley. I'm with the Software Engineering Institute at Carnegie Mellon. This morning, I'm joined by Jay Marchetti, who's also with the Software Engineering Institute, and Cecil Odell, who is with NASA's IVNV. We're going to discuss a methodology for addressing code quality issues in today's discussion. So our agenda: code quality risk. What's the risk associated with actual code itself? Not the functional aspect, but the structural aspect of that code. We'll talk about the applications and findings for a recent NASA flight software example. And we're going to talk about some of the extensions and future directions for code quality analysis. So risks associated with code itself. The actual risks to projects are many. There's scheduling risks and budget risks, operational risks, a lot of programmatic risks, but there's also risk in the software. And as organizations mitigate those risks from a variety of different ways, so too must it mitigate the risks associated with poor software quality. So let's take a look at where poor software quality comes in and some of the costs associated with it. As we can see from this list here, poor quality code is hard to test. It's prone to critical failures and crashes. People might often call that code brittle. It's tough to extend for new capabilities, so the maintenance of poor quality code becomes very difficult. It can be plagued with latent defects, and it's hard to change without adding new defects. CISQ recently discussed in one of their articles, a January 27th, 2021 article, the cost of poor quality of software in the United States, and they estimate that about $2 trillion is spent on poor software quality. So our mission is to characterize this risk, these types of software risks for a given code base. So we first start with some standards. We're not the first to look at this. We're looking to aggregate what exists in existing standards. IEC has a variety of standards, 9126 and 20010, the software product quality standards. There's also the Hersteller Initiative, HIS, so in the European Automotive Consortium. There's also software safety and software security standards. So let's dive deep inside of IEC 9126 and 25010. We take a look here at some of the areas that they're looking for: capability, compatibility, security, reliability, usability, performance, efficiency. Collectively, those areas are what 9126 believes to be the most challenging areas of software quality. We'll use that and then expand on it.
Hi, I'm Jay Marchetti. I'm with the Software Engineering Institute. So leveraging the structural perspective that Mike talked about from ISO and the other code quality standards, SEI uses a taxonomy of 6 aspects of code quality, shown here in blue, each comprised of numerous focus areas shown beneath them. Again, we're interested in structural quality, that of the code itself, rather than functional quality or how well the code satisfies its requirements. Our methodology uses an extensive set of code level questions, which the analyst answers by using static analysis tools and reviewing a subset of the code to arrive at a score in the closed interval 1.0 to 5.0, representing an estimate of the risk for each focus and aspect. So let's first look at the context for SEI code assessments in order to better understand the methodology that we'll then go into some detail on. The usual context is for an existing code base, not greenfield development, critical systems, whether mission, safety, or security critical. Embedded systems coded in C or C++, typically on an RTOS or Linux platform. code only, so we don't generally have to have the requirements or other documentation, though of course we would welcome them if we can obtain those. We also don't assume that we have access to the developers or subject matter experts on the code. We use multiple static analysis tools, metrics, and critical system coding standards, and have the analysts put eyes on code on a targeted subset of the code base. And we do this for classified and unclassified code bases. So next, let's take a look at the details of how we assess code quality risks. So the methodology centers around CREW, the Code Risk Estimation Worksheet, which is a multi-tab Microsoft Excel worksheet. Some of the overview points on CREW, it was originally based upon work that we did for the Navy's Zumwalt class guided missile destroyer. As I'd mentioned, risks are assigned within the interval 1 to 5, and each aspect and focus grouping within an aspect has an associated analyst tab containing relevant detail-oriented questions. There's nearly 500 of these detailed analyst questions with relative weighting, and they're posed as one of 3 types: either requested metrics, values that are pretty much straight out of static analysis tools, requested quantitative estimates from the analyst, which usually require additional calculations to be made, or qualitative analyst inputs from a drop-down selection list. And the analyst responses are normalized and combined by CREW into a 1 to 5 risk value for each focus. And then each of those focus risks are rolled up for their particular aspect and rolled up further for an overall risk estimate for the code base. The inputs tab of the CREW worksheet shown here tracks our receipt of inputs that are needed for the assessment process. And the top priority ones are at the top of this list. Of course, include all the source code, build scripts, make files, a build specification, a complete build log showing the developer's build of the system and any warnings that might have been thrown, a complete list of all compilers, linkers, target RTOSs, host OSs, basically all the tools used to both develop and run the code in its target environment. The unit test code, any mocks or test framework code that comes along with the actual code base. And we would also like to have a VM that shows, verifies the build and how it is run by the development organization. The process flow for CREW code analysis is shown here, where the basic flows from top to bottom, and then within each vertical level from left to right. So we start with the inputs that I had mentioned. We move into tools, multiple static analysis tools and analytics that we've developed. We have the human analysis portion of the assessment, where we bring in the CREW worksheet, and then we use the CREW worksheet to develop the outputs, which are generally either results briefings and or a report. So the CREW worksheet is intended as a guide for the code analysis by codifying several important objectives I'd just like to touch on briefly here. The code analyst is presented with questions to consistently direct the analysis. using multiple static analysis tools and by reading a subset of the code. The questions are intended to be static analysis tool agnostic. And as I'd mentioned, it's the framework that we use is directly applicable to critical embedded systems coded in C and C++. The questions are aimed to objectify the risk estimation as much as possible, and no question or metric is really make or break. It's a statistical estimate of risk that we're after. The questions of different types are combined and scored to derive a resulting risk. And we try to hold the scoring and questions constant in crew over time so that we can begin to gather some historical perspective on the code bases that we've used this methodology on. So here we see the top portion of the crew worksheet, results tab. And after the project information preamble and the usage key, about 2/3 of the way down, you see two aspects that are visible here. They're shown in blue, architecture with a score of 2.4 and standards with a score of 2.6. Also note the constituent focus scores under each aspect. Recall that these scores are in the closed interval 1 to 5, but also all scores are shown with a color scale indicated in the usage key. Here we see the middle portion of the crew results tab showing the maintainability and fault tolerance aspects, as well as the focus scores for each. And last, we see the bottom portion of the crew results tab showing the security and testability aspects, as well as the total risk score averaged over all 6 aspects, which is 2.5 in this example. Note that the testability aspect scored at 1.9 is, like all the other aspects, simply the mean of its focus scores. Specifically, the complexity focus is scored at 2.8 under testability. So let's go to the testability tab to see how this score results from code level questions that are posed to the analyst. Here on the testability tab, we can see at the left the 3 focuses for testability: unit, regression, and complexity. For each focus, we also see the code level questions that the analyst will answer at the right. For complexity, the analyst answers are scored and they drive the resulting focus risk score of 2.8 in this example. So recall that there's 3 types of analyst questions: metrics, estimates, and selections. Here in the maintainability tab, we can zero in on an example of each. Metrics are numeric values that usually come straight from a static analysis tool. Estimates are numeric values that typically require combining static analysis outputs or other calculations. And finally, selections are the analyst's best answer from a drop-down list after reviewing the relevant static analysis outputs and source code. So each analyst answer is normalized into 3 component levels of risk: low, medium, and high, using concepts motivated from fuzzy set theory. Values were chosen that transform the x-axis ranging from 0 to 1 for each specific analyst question, as shown here for cyclomatic complexity. In this case, for scoring cyclomatic complexity, we might choose a gain of 15 and an offset of 5 to transform the membership functions range from 5 to 20. So for each analyst question, crew specifies a gain and offset to set the risk thresholds in this way. When the analyst enters an answer within crew, it's applied to this scaled risk membership function to compute the low, medium, and high components of risk. For example, let's look at the SLOC or source lines of code question. In this case, we've scaled the x-axis to cover from 0 to 1 million lines of code. If our static analysis tool reports, for example, 350K SLOC, then we see that the low, medium, and high components are computed by crew as 0.25, 0.75, and 0, respectively. Finally, crew combines all the components, that is low, medium, and high, by averaging them for each focus. Then a CRISP composite risk score is computed for each focus by taking the dot product of the 3 average values with 3 singletons, as shown here. The next, let's take a look at the resulting outputs that we typically brief to our customer. We usually start our briefing by showing the crew results tab with the overall and component aspects and focus scores. Then we cover the main positives as green bullets and areas for improvement as red bullets, as discerned from the crew results. And before walking through each crew aspect to brief specific code samples or static analysis outputs that exemplify the scores, we provide the bottom line up front or bluff chart. This indicates what our risk assessment shows should be maintained in the code base and what can be improved.
Thank you, Jay. As we talk about crew, we talk about some of the extensions and the future directions of where we'll take this tool. So to continue to improve our process, we are creating new analytics to analyze the actual source code and the output of static analysis tools. Our intention is to take human subjectivity, some of our most senior analysts, to pull them out of the equation and let analytics themselves drive the raw output that goes into the scoring tabs within crew. We also intend on mining additional standards, such as the AutoStar standard and others, to ensure that the coverage that we have in crew is complete. And as you can imagine, we look at a lot of source code from a variety of organizations. And over time, we're analyzing the results of our process to ensure that the scoring parameters make the most amount of sense per given code base. So we're continually improving the tool.
Hello, everyone. My name is Cecil Odell. I'm a software engineer with NASA IB&V. I'm currently representing our SSO outreach team, which I am the technical lead for the NASA side of adapting this code quality risk assessment process. So we're looking at this process to help us identify opportunities to improve NASA mission code, very similar to what was shown with OpNav. We're looking at, determining ways to potentially automate some of the questions so we could apply it on a larger scale to, potentially reach more missions more efficiently. So this implementation has been broken down into a 3-phase process, the concept and research phase, which we wrapped up in December of last year. We're currently working on a combined phases 2 and 3 to prototype and test out the adaptation of this capability with a pilot project on the NASA side. Some initial results. We looked at, like I mentioned earlier, we looked at which questions we thought we could automate based off of our subject matter expertise at NASA IVNV, as well as our tool availability. So we looked at the questions individually and gave an assessment of whether or not we thought they were fully automatable based off of our own internal capabilities, whether or not they were partial, which means, some combination of tool and analyst judgment, or whether or not they were completely based off of analyst judgment. So as you can see, we've broken that down by those specific categories as well as by the individual aspect areas. We feel like this information will help guide us towards, seeing that, if we apply this to multiple mission critical NASA missions, where are we spending the most time, or how can we, potentially speed some things up if, we want to apply this on a wide scale with limited resources. But, we do think that this code quality risk assessment is a very powerful process, and we're looking forward to add it to pre-existing NASA risk assessment processes. We think it would complement some of our functional risk assessment processes extremely well.
And so in summary, our SEI's code risk estimation worksheet is being utilized to improve code assessments through thoroughness, levels of objectivity, consistency, traceability, and the adherence to standards. The resulting estimates provide stakeholders with an easy to understand snapshot of risk level that's inherent within their code base. Thank you all for joining us, and we hope you have a great day.